Are you able to hear us, David?
Yeah, I can hear you far, but yes, I do. What about you? Can you hear me?
Yes, yeah, we can hear you loud and clear. Hello, hello, David. This is
Yeah.
Sudhir here. Nice to meet you.
Hi. Yeah, likewise, likewise. So just tell me how you would like to proceed.
Okay, sure. Are we ready to proceed? Why don't we do an introduction?
Yes, sir. I am about to. Okay. Okay. Very good morning, sir. And for the today's session, I welcome Professor David Soldani, sir, who is working in Rakuten Mobile, Australia, and he has 25 years of experience in information and communication technology, having held senior management and executive positions in global organizations for more than 20 years. His contributions extend to both industry and academia. He has served in various roles at Rakuten, Nokia, and Huawei, including Global Head Technology, CTO, and CSIO. Further, he has held positions as an industry professor at esteemed universities such as UNSW, University of Surrey, and UTS. During his career, he has owned significant businesses, reporting directly to senior management across Europe, China, Japan, Oceania, and Asia Pacific region. He has engaged with stakeholders from private and public sectors at various organization levels. In these capacities, he has been responsible for technology and business strategy formulation and implementation, aligning with the board of directors. His accomplishments include 500 plus R&I and sales projects for ICT systems and services. These efforts have resulted in the delivery of over 1,000 quality outputs and encompassing strategic research, innovation strategies, business plans, cases, papers, patents, standards, and POCs. We welcome you, sir, for the session.
Yeah, thank you. Thank you for having me. And I'm particularly thankful to Sudhir. He is a very distinguished person I've been working with. And thank you again. And also thank you for the comprehensive introduction. Yeah, and so we discussed about the sharing some views which are my views. They do not necessarily represent my organizations on the cloud and AI native aspects of 6G. And I've had the power by eBPF. So I'd like to go through some basics and definitions, but then showing you some applications and results we have obtained with the theme. And then I will conclude by, of course, summarizing the points, but particularly showing you where the most important advancements, not only in the direction of 6G as a workload, but also the underlining a platform. Okay, so it's a very, very huge, broad topic. I try to stay focused and on the key points so that I can deliver what I think should be in focus for the industry and for academic, but overall innovation and research community at the global scale. Right, so I thought perhaps I start with a definition because sometimes we use different terms and we are having a different understanding of what the cloud native approach is all about. So when we say that our network or our workload, this case, say 6G is cloud native, it means that it is designed and built for running on scalable, resilient, flexible way of implementations which is optimized for cloud environments. It's not the vice versa. So because when you discuss with vendors, they tell you, okay, look, you need to buy my infrastructure, and then my infrastructure will deliver the best performing 5G, 5G advanced, the mobile communication system. Is absolutely the contrary. What we seek here is a network, cloud native functions that do run on my cloud native platform, and not the vice versa. So that means the design has to be such that with a simple command or a process, I can have any sort of network function on my infrastructure, which I'm also using for running other type of workloads. And today I will show you how we interact with artificial intelligence. Okay, then there are many details within the scope of this definition. For instance, we are having all these kind of characteristics, and here I am particularly mindful of the microservice architecture, so that we expect a very small type of images, and has to be containerized, and then with ability then to run on a Kubernetes platforms and its evolution. It has to have capability of supporting eBPF, and yeah, compatible with DevOps best practices, thinking of continuous integration, continuous development, which I can do in relation to the feedback I'm receiving from my operational team. I should be able to provision it very easily in an automated manner. Terraform is just an example here. And other characteristics of the workload has to be AI ready, which means my AI workloads to exchange services with the 6G workloads, not only thinking about 6G images or cloud native functions supporting AI. Actually, most of the AI thinking of Gen AI will reside outside the 6G cloud native functions. So functions that will deliver connectivity between 2 points or more points. API driven, that means I need to be able to communicate with very simple API and exploit any sort of capabilities, including exposing them externally. I'm not only thinking about connectivity related capabilities like network slicing. I'm thinking immersive services you could offer through the next generation mobile communication system. Okay, there are many benefits, and I will, anyway, I'm recording this presentation, and I will also share the video. So the key point is that we want to have something that scales, as to be always available. I need to be in production extremely fast. It has to help me reduce my costs, and has to be portable, so I can run it across any data center and cloud native platforms I have in production. And then, of course, it has to support security and isolation. That, of course, that comes particularly with the introduction of Kubernetes. Okay, where are we today? Where my vision is, or where are we going here? So today we are here. That is the most advanced infrastructure deployed globally. That is the Rakuten mobile communication system in Japan. You see here the operator is extremely young, like it's around 5 years old, the operator, looking at the 5G services. And today we are having in production more than 350K cells on an end-to-end virtualized infrastructure. And we are growing as we speak. We already exceeded 8 million subscribers and reduced our churn and also increase the ARPU because people, they receive excellent quality services as various measurements by, for instance, OpenSignal demonstrate. So the network consists of three main data centers. We have the so-called CDC. Sorry, here it would be the central data center, CDC, central data center, where we run the core network and other service workloads. And then we have the radio access, which span across two types of data centers. We have the virtual centralized unit, which run on regional data centers. And then we have a virtual distributed unit that are running at the edge. We are now replacing servers with our next generation distributed unit hardware to improve performance and also further reduce costs. And here you have example of radio access antenna. As of today, we have demonstrated that this system not only shows an amazing flexibility and ability to integrate communication services, but any sort of application, but also allows us to reduce CapEx and OpEx compared to traditional implementations of 40 and 30% respectively. So based on this architecture, I have now generalized it a little bit also to give you a sense of economy of scale. So central data center, typically we are on 10 plus sites, regional data centers maybe up to thousands, and then a far edge nodes, basically the one where the virtual distributed unit carrying the radio interface stack, protocol stack, maybe 100,000 more sites. As you can see, we are already more than 350K cells. You may calculate, divide by 3 on average, and that basically the range of magnitude of the infrastructure that you're having in front of you. Okay, then, I mean, there are many benefits, and some of them are shown on this slide. Now, moving forward, how I do see the network evolve. This is a high-level representation of a 5G architecture, reference architecture, where, let me take the other, maybe the last point, where you have already an infrastructure which is virtualized over traditional virtual machines. It is the old way of running workloads. And this represents the shift towards having 5G virtual network functions on Kubernetes. And since these functions were not designed by Etsy and other contributors and organizations for running on containerized environment, we had to introduce an additional software component. You want to call it plugin or project, denoted as Nephew. So you might have heard about Nephew. So what Nephew does is making Kubernetes the de facto standard for declarative management within this telecom infrastructure. And it establishes among the different players, which is basically now the standardized manner to do it, common templates that conform to both the O-RAN Alliance specification and 3G specifications, looking at automation of configurations across the entire infrastructure. So you may see here the various templates for cloud infra resource automations, both on public cloud and private cloud, workload resources, automations, and then workload network functions configurations. Have we solved the problem? Absolutely not. So my view is that we need to shift from this kind of deployment to something that will lead us to a cloud native functions. So I don't want to use projects such as Nephew or any add-on capability on my platforms and requirements towards the workloads. I simply want to have my workload, which has been designed to run on Kubernetes. And the network will be massively simplified. I'm also expecting that these functions will benefit not only of the capability of the Kubernetes in terms of container orchestration, therefore cloud native function orchestrations, but also of eBPF. I will explain what the eBPF is. eBPF is a VM or the Linux kernel that can provide services to the application running on top of the host operating system. Why are we doing this? Why I am pushing this? And in addition, I would like to have that these functions are completely decoupled from the underlying infrastructure. So I'm vendor agnostic. So I don't want to have my cloud native function running on any specific vendor infrastructure. But I simply want to build my infrastructure to run any sort of applications. And to me as an operator, 6G is nothing else than an applications that deliver connectivity services. That's it. It could be a web server, it could be an AI function, or it could be a function that deliver connectivity between two packets, the one originated from the mobile station and the other one coming from the internet, from other mobile or somewhere else. So the next step is that what we need to make here is that 6G, we need to make 6G work with AI. And AI, when we think of AI, there are two AI disciplines or type of models, or you do have the traditional AI, which are discriminative, which basically are around pattern recognition. You may think of neural networks and related application, could be supervised and supervised, it doesn't matter. They are on top of the training data, and then they go ahead whether you supervise them or not, but they are after discriminating the inputs they receive. And then you do have the generative AI, which I think is definitely the way forward, although the two technologies will complement each other and coexist, is the generative AI. Generative AI, the difference is that Gen AI, given the input data, the training data, what they do, they sample the data, and then they embed the data. There are various types of representations, and create the correspondent so-called hidden or hidden space or latent space, which is then resample to reproduce something that represent the input. Okay, that's the generative AI. That's the novel aspects of this service. This is our example applications, which I would like to have on in my clusters and coexist with 6G and exchange services. And there are many, many, many use cases. I have just one slide where I think are the most important application. So this kind of this slide, although high level, it captures pretty much all the concepts I'm presenting today. And the key here is that I am building an infrastructure or evolving my infrastructure to run any sort of application. And 6G is nothing more, absolutely nothing more than an app that runs on my cloud containerized system on Kubernetes and related plugins, where I can also host different type of application, such as, for example, 5G, or there could be IMS services, any sort of web-oriented application, and including AI models. Okay, then the other important requirement is that the 6G and AI, both thinking of them as applications, they comply with the so-called DevSecOps process powered by eBPF, where I have an automated manner to constantly improve my software, create images, containerize them, and then put them down into my infrastructure. So this continuous integration, continuous development, deployment will allow me always to upgrade my system and move towards the directions of improving my KPIs, which is not just about improving performance, but I need to think also running applications which allow me to monetize. I need to be efficient to reduce my costs, and then I need to be on a system, on a network that is absolutely always available. So it helps me to reduce the risks. Okay, so that's basically concluded the high-level part. So I have now a few examples of applications starting from AI. Then I will introduce a bit what the Kubernetes is, eBPF, and then some example what we have achieved with my team. Is there any questions so far? Okay, if no question, I think we can go through the AI. And AI, in my view, there are three, thinking of 6G or mobile communication system in general, there are three main applications. So why do we need generative AI? So the first application is around compressions and semantic communication. And as I said, by sampling and then the hidden space, the latent space, I have ability to reduce the amount of data to be transmitted from A to B. And at the same time, I have ability to reconstruct it. So I have ability to transmit simply the meaning, and then I have this model that helps me to reconstruct information, therefore reduce the bit rate for delivering the same amount of data. And there are various models that are listed in here. Then another important application is ability to generate synthetic data, an event. So it depends on the application you think of. And here you're having like generative adversarial networks, but also variational autoencoding, JEPA, can be used to achieve this goal. And then the last, but not least, actually is where my team is currently focusing, is the ability to predict. So predictions are not just trends like using LSTM networks, neural networks, or analytics where I could see that something grows. No, I need to have ability to learn embeddings and that to predict the relationship between variables without reconstructing data explicitly. So I need to have algorithms which are after, and they have ability to predict the consequences of a certain action, like our brain works. And this is, for example, the joint embedding, JEPA. And we are currently using it for predicting anomalies on VAF and other type of logs. Okay, now just to go quickly through how the Kubernetes works, and to get to give some feelings of the complexity of the network and why I'm also pushing that the 6G here represented by this image you see here on these different nodes has to be simplified, because many capabilities of 6G, thinking of security for making this particular virtual function communicate with another virtual function within the same domain, doesn't need to be encrypted. I can do that through my Kubernetes infrastructure. Also, the identity of certain function could be extracted down in the infrastructure. I don't need to make any kind of sophistication within 6G. So that shows you how a cluster is built and the different capabilities of Kubernetes in the control plane and user plane. So typically the implementation is that you're having, if you are on public cloud, you typically reserve, unless you're using like the Google, Amazon, and other web scale available platform, but if you even rent VM instances, you will dedicate one VM for each node. This is a cluster of 3 nodes. You have a master is on VM, and then you have 2 nodes with the 2 corresponding VMs. If you think of a deployment on a real network, then you will have dedicated servers with and without GPUs. So for example, in this case, I'm expecting that this node, this server will also have 1 or 2 GPU cards. Okay, now I have details how the cluster work and the workloads work and communicate. Yeah, I will need 2 to 3 hours to explain this. Yeah, I am moving, but you can see it's extremely convoluted, the communication, depending on the container networking interface you're using. If you are, for instance, deploying Calico, we know eBPF, then if you want to expose certain services to reach the container, you need to simply establish various type of tunnels, and that gives you an idea of the complexity of the system. Okay, in this case, it shows what you need to have in place within one cluster. It is just one cluster, not between clusters, but one cluster. So it's 3 servers for one application. This pod network, this pod here, to communicate with this pod here. So if you are in this pod, if you have this, think of AMF, and then wants to this AMF communicate with the SMF or other functions, he has to establish all this transport communication, including a tunnel between nodes. It's extremely complicated. And then above it, you need to have running the GTP tunnels, and the GTP tunnels will allow you maintaining the IP address of the mobile phone, for example, while it moves across the infrastructure. Introducing eBPF, the system is massively simplified. So Cilium, for instance, removes the IP tables inside the nodes and replace them with eBPF maps. So today, eBPF maps, we have massive advantages to move packets across the Linux kernel. So from the network interface cards to reach up the applications and vice versa. Now, I wanted to show, this is what we are currently doing with my team, just to make you understand really the importance of being cloud native, that everything goes cloud native, including AI. AI, language model, large language model, or large model, generative AI in general, we run on Kubernetes. There is no other possibility. That's my view, because it's so expensive that you can't simply dedicate hardware to one specific application. So you need to have an infrastructure where you just deploy your model, you train your model, you may swap the model, all done in a sort of real time. And that is what Kubernetes allows you to do. I have just presented you how eBPF works, what it is. So eBPF is just a VM of the Linux kernel that allows me to program the Linux kernel without touching the kernel itself source code. And this is done by by compiling and injecting the programs I want to run in the kernel and attach them to specific hooks. So by attaching them to the specific hooks, then my program is executed when that particular event is triggered. So then I have ability to extract the packets. I can ability to, for example, drop a packet. I have ability to detect a particular system calls and monitor whether somebody is changing files and so forth. So there are many applications we can do. It also does support, in a way, the service mesh. It supports like encryption, and it is ideal for security tooling. We have created our own platform, denoted as Sauron, and Sauron today runs on RMI network, and our agents, so our eBPF programs, are injected across all domains and on any network element which runs a particular Linux kernel version. So wherever we have the Linux kernel, we have ability to instrument the Linux kernel. Therefore, we have ability to run our agents, and the agents allow us to make measurements across the transport network layer, observe what's happening in the network elements, as well as enforce a specific security policy. We have 3 use cases that we have implemented. So the first use case is on network performance. So by deploying our agent on different routers or servers, we exchange packets and we extract a delay in using active measurements, delay, jitter. We start the quality of service, and we can also detect anomalies on it. We have ability to extract the packets, so we can monitor and get rid of our network interface probes. Security as well, we can monitor what happened and determine any sort of anomaly in terms of access to network elements or access to our data. And we also have ability to measure the consumption of each of the workloads running on those nodes where our agent is also deployed. We have achieved very interesting results. So here you have 2 examples of anomaly detection using our agent. The first one was on security anomaly detections. And I can go, for example, here. You can see that using our algorithms, extract this information, and then the AI, we can determine the anomalies in terms of username. So when the people log in into the authentication servers, we can detect immediately where that behavior is normal or abnormal. And it works very well, and we are now in production. The same thing applies to the deployment we had on transport. Our agents allow us to measure the delays end-to-end and hop by hop by generating these synthetic packets. We have implemented to approach the one is statistical approach, but also using discriminative AI. It is a result of using DBScan. So through DBScan, we went after 2 features. The one was on latency, and the other one was on jitter. And as you can see from this graph, we have ability to determine immediately if there is a problem across the communication between 2 or more peer entities. Now, I would like to conclude this talk just to show you what I think it's key, and what kind of infrastructure we need to have to efficiently running not only the 5G or 6G workloads, but any sort of workloads. So where we are working now is in this kind of reference architecture. So we have our agents where I have ability to deploy all over the places. So I have agents that I will use for security, other agents that will allow me to extract packets, and then other agents that will allow me to measure the performance across the network. So all this information could be put together along with other information on which we run our algorithms. And you have seen the examples of anomaly detections. But beyond that, what we're doing now, because there are other source of KPI that we want to take into account. For instance, if you want to put in relationship the performance experienced by the end users that you can capture through 3GPP KPIs and what happens in the transport network layer, what we are building now is a RAG model, so retrieval augmented generation model, where we will have ability to look into both type of logs, and by exchanging this query from the end user prompts, we will have ability to navigate it through and detect where the problem is and troubleshoot the cause of this specific lack of network performance. Another area where we are working on now is where to run efficiently our workloads. And so that means I need to work and run on Kubernetes all my models and expose the capabilities of my models to whatever the consumer is. It could be like cloud native functions, 5G, 6G, but it could be also a person, like people that are in the field, or could be people from operations, or it could be other agents that they can use this information for further analyzing it and then propose or even take action. So that is the first important things that will evolve, and this is where we are currently focusing. Beyond that, we need to look at how the system overall has to change. Now, if you look at how the cloud native platform works today in Kubernetes, today you need to give to each node one server. There is no possibility to share these resources between servers, although they allow you to horizontally and vertically scaling the workloads depending on the resources you are having on that node. So that means you could add replicate the same cloud native function on the same node, or you could replicate this cloud native function executed, scheduled on a different node. Okay, but we need to go beyond this, because by using this kind of configuration, if you think of utilizing, for instance, GPUs, which are extremely expensive. So you may think of $25K US per card. So you need to use it. You need to make it available, right? In order to achieve this goal, what we're looking now is into a new technology denoted as composable disaggregated infrastructure. That technology, which is, by the way, transparent to the Kubernetes, it will allow us to share the resource pool between nodes, you see here. Beyond that, thinking of the number of clusters, we do have thousands of clusters on RMI infrastructure. We want to have a single access to all cluster, and we are thinking of cluster peering. So in the end, you will have ability to not only share the resources within one single cluster, but you may also deploy your workload, thinking of 6G workload, AI workload, and then distribute the load across all cluster you're peering with. And then by doing this, will allow us not only to achieve an horizontal vertical autoscaling, but also we will have ability to autoscale the entire cluster, which I can move from one data center in another. And then the last thing we are looking into now, it is the resource sharing, so that the DRA will allow me to share the single GPU. I can schedule this direct resource accessibility. I could even achieve the level of sharing a particular GPU. So that would allow me to share GPUs at the granular level with my applications, accessing these resources. At the same time, I can share these resources between my nodes, and at the same time, I can share the resources of my clusters with other cluster. So that's pretty much what I wanted to present it to you today. We have published a few papers, one more coming on anomaly detection that shows some applications of AI and discriminative AI and Gen AI on cloud native system is coming. I think next week will be published at the Mobile World Congress. So I'm sorry for the inconvenience or connectivity and the problem we had, perhaps too much material. We can have now some questions, and if you want, we could also have some follow-up discussions at a later time.